question about playing Monopoly. If you get more doubles than any other player, then you will lose. Or if you lose, then you must have bought the most properties. True or false? We will answer this question in this video, and we won't need to know anything about Monopoly. And I really want to emphasize that. You don't need to know anything about Monopoly to answer this question. Instead, we'll look at the logical form of the statement. We need to decide when the statement P implies Q or Q implies R is true. That's the format of what I just said. Using the definitions of the connectives in previous videos, we see that for this to be true, either P implies Q must be true, or Q implies R must be true. Those are true if either P is false or Q is true in the first case, and Q is false or R is true in the second case. So yeah, it gets kind of messy. Luckily, we can make a chart to keep track of all the possibilities. Enter truth table button. The idea is this. On each row, we list the possible combinations of T's and F's for true and false for each of the centennial variables, and then mark down whether the statement in question is true or false in that case. We do this for every possible combination of T's and F's. Then we can clearly see in which cases the statement is true or in which cases the statement is false. And you can see some of these truth tables down here for now to kind of get a sense of what I mean by that. For complicated statements, we will first fill in values for each part of the statement as a way of breaking up our task into smaller, more manageable pieces. Since the truth value of a statement is completely determined by the truth value of its parts and how they are connected, all you really need to know is the truth tables for each of the logical connectives. And so here they are. These are all of the truth tables for the logical connectives. So again, you see for each truth table, we list off of all the possibilities for P and Q. P and Q could be both true. Maybe P is true, Q is false. P is false, Q is true, or P is false and Q is false. These are all the four possibilities here for how P and Q can be oriented, and we can take a look at what P and Q would be given those inputs. And so if you want to think about this, you have here on the left side some inputs, and on the right side you get some outputs for each of these instances. So this is P or Q, that's P implies Q, and that's the biconditional. None of these truth tables should come as a surprise. They're all just restating the definitions of the logical connectives. Let's try another one. Let's make a truth table for the statement, not P or Q. And I'm gonna, actually I'll just scroll down. So to do this, we're first gonna list off all the possibilities for the atomic statements P and Q. And then we'll start working through the logical connectives. So P and Q could both be true. We can have true and false. We could do false and true. And then false and false. And now we're going to look at, we can't quite look at not P or Q because we don't really know what not P looks like. So let's actually now do a column for not P. Not P is just the opposite of whatever P is. So if P is true, then not P is false. If P is true, then not P is false. If P is false, then not P is true. And if P is false, then not P is true. And now we can look at not P or Q, which is just looking at these two columns. And we're seeing if one of them is true. At least one of them is true. The first row, yes, Q is true, so this is true. Second row, they're both false. Third row, they're both true, so this is true. And then fourth row, not P is true, so that's true as well. Okay, so let's note that this statement is not the same thing as not P or Q. That's a different statement. The negation belongs to P alone here. Okay, so I want to mention we added a column for not P to make filling out the last column easier. The entries in the not P column were determined by the entries in the P column. Then to fill in the final column, we looked at the column for Q and the column for not P and used the rule for excuse me, for the or symbol. I can't speak words right now. Let's answer our question about monopoly though. And let me make some room here. So we're going to analyze the statement, if you get more doubles than any other player, you will lose, or if you lose, you must have bought the most properties using truth tables. Okay, so to do this, what we're going to do is we're going to let this portion of the statement be P, and then let's let this portion be Q, which means that this portion is Q, and this portion we're going to let R be R. So here we have P, which is you get more doubles than any other player. Q is you will lose, and R is you must have bought the most property. So let's represent these in a truth table here. So we're looking at P implies Q, or Q implies R. Now to get this in a truth table, we have P, Q, and R. Let's write out all the possibilities for P, Q, and R. They could all be true. We could have true, true, false. We could have true, false, true. And true, false, false. I need more room. We can have false, true, true. False, true, false. False, false, true. And false, false, false. So these are all the possibilities for Q and P, Q, and R. Now, let's take a look at P implies Q. We can work with that. So here we're only paying attention to the first two columns. Now, P implies Q is false when P is true and Q is false. Otherwise, it's true. So here it's true, here it's true, here it's false because P is true and Q is false. Likewise, that's also false. I need more room. This is, let's see, that's true. Even though P is false and Q is true, that's not the same thing as P being true and Q being false. Still true. Therefore, that's true, and that's true. All right, next portion. We have P implies Q. Let's look at Q implies R. So now we're only looking at the Q and R columns, and we're seeing if Q is true and R is false. If Q is true and R is false, then the whole thing is false. Otherwise, it's true. So that's true. This is false because Q is true and R is false. This is true, true, true. It looks like false, true, true. Okay, we're almost done building our molecular statement using all these complex logical connectives. So now we can look at P implies Q or Q implies R. In order for this to be true, it has to be that for these two columns, they must be true as well. Both, or one of them has to be true at least. And so this is true, this is true, this is true, this is true. Let's see, do we have any more truths? Yes, we do. That's true, that's true, that's true, and that's true. It's always true. So what does that mean? That means P implies Q or Q implies R is what's known as a tautology. It's always true. Now, if it's always true, that means the statement that we're trying to prove is completely true. Now, what are we trying to prove? We're trying to prove that if you get more doubles than any other player, you will lose, or that if you lose, you must have bought the most properties using truth tables. So that means the statement about monopoly here is completely true. I don't know anything about how monopoly works or the rules, but I can guarantee you that this is true. This statement here is true. So that's how we can use logic to our advantage. We don't even need to know about the context. We already know this is true. The statement about monopoly, though, is an example of a tautology, a statement which is true on the basis of its logical form alone. Tautologies are always true, but they don't tell us much about the world. No knowledge about monopoly was required to determine that the statement was true. In fact, it is equally true that, for example, if the moon is made of cheese, then Elvis is still alive, or if Elvis is still alive, then unicorns have 5 legs. It's the exact same logic, exact same structure in terms of logical connectives, so more or less the same structure of a statement. And so yeah, it's true. The statement is true. It might have components that are incredibly false, but the statement overall is completely true nonetheless. It's just kind of meaningless. Tautologies are kind of meaningless to say. So for example, this pen is either black or it's not black. That's great. You gain no information. It's completely useless. But they're still kind of interesting and you should know what tautologies are. Anyways, thanks everyone, and I'll see you in the next lecture.